So in this section, we're going to be graphing systems of linear inequalities, which it's very similar to doing one. We're just going to have two now. So first we'll just go back to how we would graph one inequality, which back when we did this the first time, we graphed it just as if it were an equation. So x minus y equals 7. At first you don't really pay attention to the inequality symbol. So what we're going to do here, you have a choice of how you want to actually graph this line. You can use a table, which likely you won't do. You could use x and y intercepts, and you can use slope-intercept form. So since it's written in standard form, it actually makes the most sense to use x and y intercepts. Remember that to find an x-intercept, you replace y with 0, which would just make it x equals 7. So that's actually the x-intercept. So you would just go over 7. 1, 2, 3, 4, 5, 6, 7, and you would put a point. And then to find the y-intercept, you change x to 0, but that would actually make it negative y equals 7, which would make the y-intercept negative 7. So that would be down 7 spaces on the y-axis. So that would be down here. And we're going to connect with a line. But in this case, before you actually make the line, you have to go back to the inequality, which is greater than, and if you remember, that actually means you're going to have a dotted line. So when I connect, instead of drawing a solid line, I draw a dotted line. And then I want to shade this inequality. So I would pick a test point. If possible, you want to pick the origin, and I can because it doesn't land on the line itself. So if you replace both x and y with 0, because that's according to the origin, you'd end up with 0 is greater than 7. And 0 is not greater than 7, so that means 0 is not part of the solution. So we showed that by shading in this side, the opposite side that doesn't have the origin. So that was actually section 6.7 of chapter 6. Now all we're going to do is we're going to take this other inequality right here and we're going to graph it, but just graph it on the same coordinate plane. So I'm going to do it in blue. And this one I would still use x and y intercepts because it's in standard form. So if I change y to 0, then 2x equals 6. So the x-intercept is 3. 1, 2, 3. And if I change x to 0, the y-intercept would be 6. This time, because the inequality has that or equal to symbol, when it's time to connect, I'm going to connect with a solid line. And now, when I go to test the origin, which you can still do because it doesn't land on the line, it's on one side. If you replace x and y with 0, you get 0 is less than or equal to 6. And that's true. So the blue one I'm actually going to shade with the origin, and I'm going to color in the blue line as if the red line wasn't even there. So I'm going to keep going, keep going, keep going, keep going, keep going. So now if you can kind of picture the overlap, I'll use yellow to show that. We're really looking, so the blue line was solid, the red line was dotted, but then the overlap's kind of in here. So just some examples of ordered pairs that would be solutions. Anything that falls in the overlapping shaded region is a solution. So for example, the point 1, 2, 3, 1, 2, 3, 4, 5, 6. So 3, negative 6 would be a solution because it's in the overlapping shaded region. The point negative 1 or negative 1, 2 wouldn't be because it's only in the blue. So it works for the blue but not for the red, and to work for the system it has to work for both. Keep in mind that the dotted line meant that points on that line don't actually work. So 1, 2, 3, 4, 1, 2, 3. So 4, negative 3, even though that point's in the blue, it doesn't work for the red because the red's dotted. But the point 1, 2, 3, 4, 5, 1, 2, 3, that would be a yes because it's in the red and it's on the blue, and the blue is a solid line. So what you're going to do right now is you're going to try these examples, these 3, and one thing that can be helpful is when you shade, like over here when I shaded the red and when you shade the other color, is to not do them too darkly, and then once you have them both, to darken the overlap a little bit. Or you can actually use colored pencils that are complementary to each other. Pause the video, press play when you're ready to check your answer. Okay, so on this first example, I just used the color dots each time to indicate which one is which. This had a y-intercept of negative 2, and then a slope of negative 1, so I just went down 1 over 1 the whole time. The greater than symbol meant to connect with the dotted line, and then because it didn't pass through the origin, I was able to test it, and it gave 0 is greater than negative 2, which is true, so the red line got shaded with the origin. This one had a y-intercept of 6, and then I can't really go up 3 over 1, I didn't have room, so instead I went down 3, back 1, down 3, back 1, over and over. Less than or equal to told me to connect with a solid line, was able to test the origin, and you get 0 is less than or equal to 6, which is true, so I shaded with the origin on that one. So some examples of ordered pairs that would be solutions. 0, 0 is a solution to both, so that works. 1, 2, 3, 4, 2, it's inside both, so that would work. 0, 6, it's in the red, so it would be a yes for red, and it's on the blue line, and the blue line is solid, so it would be a yes for blue as well, so 0, 6 would work. An example of something that wouldn't work would be -2, -3, because it's in the blue, so it would be yes to blue, but it would be a no for red, because it's not in the red. Or -3, 3 is a yes for red, but a no for blue. And to say yes, it has to be a yes for both. And then 0, -2, that would be a yes for blue, because it's in the blue shaded region, but it's a no for red. Even though it's on the red line is dotted, so the line doesn't count. This one shows both the red and the blue, so here is where your overlapping shaded region is. That's where you'd find your solutions, in here, and then also on that portion of the red line, since the red line is solid. And then down for this one, this is our overlapping shaded region, and so you have any points in here would be solutions, and then also any points on this portion of the red line. So the ones on this page are a little bit trickier for a variety of reasons. One is that there's 3 instead of 2, so if you shade all at once, it can get a little messy. And then the other reason is that it involves horizontal and vertical lines. So we'll start with y is greater than or equal to -1. Again, when you graph that, you just pretend that it's y equals -1, which means we're looking for a line that always has a y-coordinate of -1. So the easiest one to find would be down 1. That point is 0, -1. Other coordinates that also have a y-coordinate of -1 would be anywhere along this space. And if you look at all of these points that I'm drawing, like this is -6, -1, so it has a y-coordinate of -1, -4, -1, -2, -1, 2, -1. All of these points along this line have a y-coordinate of -1. And then now when it's time to connect, that goes back to y equals is a horizontal line. Anytime it's y equals, it's a horizontal line. When it's time to connect, the inequality is or equal to, so I'm allowed to connect with a solid line. To shade, you could test the origin, because the line itself doesn't pass through the origin. But if you think of the origin as a coordinate, the only part of the coordinate that has anything to be replaced is y. So you could replace y with 0, and you get 0 is greater than or equal to -1. That's true, so we're going to shade above. The easier way of looking at this is to just look at this and think, okay, I'm shading the space that's greater than -1. Your only two options are above or below. The one that we most commonly associate with greater is above. Rather than shade in this whole entire side right here with blue, what I'm going to do, rather than shade this whole thing in, I'm just going to give myself a little hint of where I'm going to shade. So I'm just going to color it in just a little bit. Just a little reminder that that side should be shaded blue. So now I'm going to go back to the next line, which I'm going to do in red, and I'm graphing the line x equals -2. So if I find a spot in the graph that has an x-coordinate of -2, that would be right there. Other points that also have an x-coordinate of -2 would be right here, right here. These are all -2, -1, -2, -2, -2, -3. All of these points, all along this vertical line, they would all have an x-coordinate of -2. And that goes back to when it's x equals, because that's really what I'm graphing. When it's x equals a number, it's a vertical line. This time when I go to connect, because it's just greater than, I'm going to connect with a dotted line. And again, you could try the origin. I just color it over in red. In this equation, the only thing that can be replaced is x, so it would say 0 is greater than -2. That's true, so I would shade to the right. Or you can think about it this way. If you're going to shade the red line, you only have two choices. You could shade it to the right, or you could shade it to the left. This tells you to shade the space that's greater than -2, and just our brains know that that's really just to the right. Instead of shading this entire side with red, I just want to picture where the overlap would be right now. So the blue line is telling me I have to stop painting here. I cannot paint below this line. That's really what that line means, because I'm shading it above. And now the red line is another border saying you can't shade to the left of this line. Everything has to get shaded to the right. So right now my overlap would go as far as this corner right here. And in reality, it would actually fill all of this space. But I don't know how much of that space yet, because I still have this third graph, and I don't want it to get too messy. So now I'm going to do this graph in green. And when I graph this, it's set up in standard form. So I'm going to use x and y intercept. So my x-intercept, if I replace y with 0 and solve, would be 4. My y-intercept, if I replace x with 0, would be 2. And just kind of a trick here, you can see the rise is 2 and the run is 4. That would simplify to 1/2, so every other point is up 1 over 2 in between, so I can actually fill those other points. If I look back at the inequality, I know that I'm going to be connecting with a solid line. And when it's time to test the origin, if I plug that in here, I'm going to get 0 is less than or equal to 4, and that's true. So if I was going to shade the green line, I would shade all of the space. Sorry about that. I would shade all of this space. The problem is, instead of doing that and then having a green shading here, a blue shading here, and a red shading here, I'm just going to look for the overlap. So this blue line, if you picture if you paint a room, you put up painter's tape as an edge. This blue line is my painter's tape, which is telling me to stop here and you can't go below. And this red line is the painter's tape saying stop here, you can't go farther left. And this green line now is its own painter's tape saying stop here, you can't go up in this space over here because you're shading with the origin. So that means the overlapping region would actually be in this triangular space. And because I can't go below the blue, you can see the blue stopping me from going below. I can't go to the left of the red, and I can't go above the green. So that's my overlap. And it came out kind of nice that it looks like a triangle, but that won't always happen. So just be careful. It's not like it always comes out to a shape. So you're going to try this guy here. So you're going to have 3 separate ones, and you want to be really careful with your shading and maybe only do your overlap. And then you're going to try this guy over here. And again, be careful with your shading. Remember that y equals what type of a line is it. You can refer to this graph up here to help you. And both of these other two are already in slope-intercept form. This one tends to give people a little bit of trouble, so be sure to check that closely when you come back. Pause the video, press play when you're ready to check. Okay, so on this one right here, here's your green line. I did slope-intercept form. The origin did not work, so the green line would really be shaded in this whole area. Just really, you can't shade on the other side of this green line. You have to shade on this side. Y is less than 4, that's our horizontal dotted line, and it's less than, so we're going to shade below. So you can't go above the red, but you also have to stop at the green. So we're kind of in this big space here. And then x is less than 3 is a vertical dotted line right here, and since it's less, we're going to be shading to the left. So you can't go above the red, you can't go to the right of the blue, and you can't go beyond the green. So it's kind of stopping you, it's keeping you in that little confined area. That blue is your solution, which is your overlapping shaded region. Over here, I'll actually start with y is less than 5, so that's our horizontal dotted line. It's less than, so we're shading below. So no matter what, you can't shade above that line. The red one was slope-intercept form, and then the origin did work, so you can't shade to the right of that line. You have to shade in the space kind of above it. And then this one, for some reason, tends to give people some trouble. It is in slope-intercept form. It's, y equals mx plus b. But since there's no plus anything, it's plus 0. So that's why the blue line starts at the origin. And then the number in front of x is just -1. So down 1 over 1, down 1 over 1, down 1 over 1. Now because the blue line passed through the origin, you can't use the origin as your test point. So I used 1, 1. So I replaced y with 1, x with 1. But since it's negative, it made it negative. And it was true. So I shaded this side. But again, you can't go past this point on the red, and you can't go above the green. So that's your overlapping shaded region.